My name is Animesh Roy, and I will be presenting our talk on evading malware analysis using reverse execution. Before I start, let me introduce you to my team. Adoksh Mishra, he is working with malware security research on Aptias. Manjas Kumar Hanawal sir, he is professor in IIT Mumbai. And myself, Animesh Roy, I am also working as research scientist with IIT Mumbai. So let's start with our agenda. We will be talking about self-debugging codes, reverse execution, further improvements on code execution using memory override, and also we'll talk about detection and countermeasures. Before we jump into our problem statement, let's talk about how an application works. Usually, the application we execute, it executes from top to bottom fashion. Okay, this is common way we execute our application. So most of the debugging tools and analysis tools are written in the same fashion. That means most static code analysis tools are designed to read code from top to bottom fashion. Dynamic analysis tools are relying on debugging mechanisms to collect data at runtime. Now, these analysis solutions could be bypassed using self-debugging techniques to defeat and change the behavior of application and also execute code in both directions. That means from top to bottom fashion, it will execute a good code, and other hand, it will execute the code in reverse order, that is bottom to top, and it behaves as a malicious or a totally different program. We are trying to explore the second option, that is execution of code in reverse order in this paper. Now let's talk about a brief of self-modifying codes. Self-modifying codes is a computer program that modifies its instruction as it executes so that overall functionality is preserved. Okay, there are two modifications. It could be local, that would be like affecting a small part of code, and then global, that will be affecting a whole code. Same, it could be persistent or non-persistent. Okay. Now let's talk about self-modifying code classes or cases. So we'll start with packers. These are the simplest one. This code contains actual payload in compressed and or encrypted form of data. Executable blob or the information can be recovered entirely from memory dump. Next, we have obfuscator. These are tools that takes an executable file as input and produce another one as output. The output binary has a different set of instruction, but overall behavior is preserved. The output binary does not have any added functionality. Self-debugging code. These programs inject extra code in their own process or forked child process and run it there. The injected code can run in the main thread itself, effectively killing the old code without releasing associated memory and metadata or in newly created thread. We have self-debugging code. This program attached to either themselves as a debugger or a child copy of the same process. Then debugger process can control the debuggy process, including but not limited to overwriting the executable codes. Self-failing codes. These programs can detect patching either in a file or in memory and can recover to the original state by reverting the patch. We will cover self-debugging code in details and present another technique that allows our malware to run in forward execution mode like all programs do, and reverse execution mode as well. The malware shows different behavior in both directions, as we can see in this image that represents running payload in reverse using self-debugging techniques. Now, we have a better understanding of self-modifying and debugging codes. Let's talk about reverse execution of code, but there are a few components that we should talk about first. Payloads. This will be the code which can be run in reverse order. That is, we're going to call them as a malicious code. In-memory execution. Self-debugging code to run payload in reverse order using the debugging mechanism. And instruction address map. This is where we can find all the corresponding instructions which are required and to allow us to execute our code in reverse order. You can see the instruction of our payload in assembly that eventually going to run the syscall and print our message, hello world. Let me explain a little bit further. So this is our assembly code. We will start from line 1 as a top to bottom code execution fashion. So from line 1 to line 7, it's a simple boilerplate. We are not doing anything there. The first line will execute on top to bottom fashion will be NOP or NOP function. That is no operation. So we're just wasting one CPU cycle doing nothing. Then we are calling syscall. Okay, so it's gonna read 0 from standard in. It will store nowhere because that's also set to 0, and then read 0 bytes. That is effectively it's doing nothing. Then we are moving RAX to 60, that is syscall exit function. Then moving RDI to 0 to parameter of exit function. And the line 16 we are calling syscall, that will just execute our exit command, return 0 to the shell and terminate the process. And that's all. But if we execute the same code in reverse order, we'll see what will happen. Okay, so first we'll start with no operation on line 21. Then we move into RDX, right? It will write 15 bytes from message buffer to standard out. And the message is on our line 2 that having a string called hello world and 2 very weird looking characters like 0AH and 0TH, that is basically line breaks with /R and /N. Then we are writing this our RSI with our message that is going to be on line 19. And then moving on RDA to 1, that will write it to standard out. We're calling up RAX to write it, and then syscall. That's going to just exit out our program and terminate our session or this application. Now, since we talk about this step, let's talk about a few more things. We'll start with stager. So stager will take our payload and address map as the input and uses that to run the payload in reverse order using self-debugging code. This is where we take control and override instruction pointers. Okay, pseudocode for stager shall look like this. So to create a child process attach itself using ptrace and load payload code using exact syscall. Then parent process wait for child process to stop, then set ptrace option to step the code one instructions at a time. Parent process matches the instruction pointer with the address map. If the address map contains offsets, those need to be changed to absolute addresses by adding a starting address with each offset. If the instruction pointer points to the first instruction where reverse execution must begin, the parent process overrides it to the point to the last instruction instead. Parent asks child process to step one instruction and break parent process instruction pointer to point to a previous instruction in list and repeat last two steps until the code or the reverse executed code ends. In this screenshot of our demo code, you can see when the hello binary was executed, nothing happened. As we already seen in our first here, it just calls syscall, moving some instructions and exiting out. And asterisk confirms our value. And when we execute the same thing with our stager, the stager is going to be executing the same binary with reverse order. So when we do that, and we execute our code on bottom to top fashion, we get our string that prints out hello world. Now, let's talk about a little bit of branches and loops. Generated assembly can be passed to jump in the opposite direction, that is forward jumps turns into backward jumps and backward jumps turns into forward jumps. If the jump is targeted to code which is outside scope of reverse execution, we can leave them as they are. On every jump, we can set breakpoints on all instruction in range which is to be executed in reverse and let the code run. Right. If it comes back to a breakpoint that we said we will start reverse execution as usual, this can be extended to mix forward and reverse execution on both points. Now let's talk about further improvements. We can improve a little bit more. For example, if you want to spoof a process, we can utilize process hollowing. We can fork to and create a new process, exec VE, a desired binary that's going to be a legitimate binary, overwriting the child process memory with our payload, and run our payload in reverse using our stager. And now let's talk about our countermeasures. Okay, we can monitor for events using tools like audit and eBPF. Okay, now these event monitoring tools does not care about direction of execution. Using of audit and OS query to monitor runtime behavior, we can figure out our reverse executable code very clearly. The other countermeasures that we should have is disabling the ptrace using YAML modules and restrict not to run any processes under root unless strictly required. I hope that will be answer all of your questions. If you have any other questions, please do let us know. Thank you for your time and have a wonderful day. Thank you.